Good evening, everybody. It's Wednesday, March 18th, and this is Nighttime Mathematics Radio. Format of the show is the same as it always is. We take questions on Twitter, so just tweet your questions to @nightmathradio.com, and we'll try to answer them right here on the show. So let's take a few minutes here to let people try to get their first questions in on Twitter, and we'll try to start answering them. For the moment, sit back, listen to some of Apple's strangest loops. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, we got one big question this week, which is going to be an interesting one to try to answer, because it's not actually a question. Somebody had a "can you help me with" sort of question. Those are always a little hard to answer. So I'll try to talk about them a little bit, and I'm going to talk about them at a lot of different levels, because these are the sorts of questions that you can ask and answer both for beginning algebra students, for linear algebra students, for discrete math students in college, and all the way up. So I'm going to talk about these at a bunch of different levels. So the question is, can you please tell me about recurrence relations? What are these things? Well, a recurrence relation fundamentally is a function that maps from the integers to the reals or the complex numbers. So instead of our normal functions that we're used to dealing with that look like f of x goes from the reals to the reals, for example, these are typically functions that go from, say, the natural numbers to the reals. What do I mean by natural numbers? Well, I mean numbers like 1, 2, 3, 4, maybe or maybe not including 0, depending on your textbook. This is a constant point of contention in math, is whether 0 counts, but we can pretend that it does for the moment. And you can write these in two different ways. You can either write them just the same way you would for a normal function. So you can say, for example, say f of 1 is equal to 6, and so on. Or you can just write them using a little lowercase number to indicate the value. And this is just old tradition when you're writing a sequence like this, because think what these really are. These are sequences. You're saying what's the first thing in the list, what's the second thing in the list, what's the third thing in the list. And there's a tradition of writing them like f sub 1, f sub 2, f sub 3, and so on, for f of 1, f of 2, f of 3, and especially when you use other letters other than f. So you see if a sequence A written as A1, A2, A3. And the cool thing is it doesn't matter which way you think of it, because a function from the natural numbers to the real numbers is a sequence of real numbers. There's no real difference between the two. So what's a recurrence relation? Well, a recurrence relation is one where instead of being given the definition of the function directly, like saying f of n is equal to, say, n minus 3, you're instead told something else. You're told an initial value for the sequence, say f of 0 is equal to minus 3, and then you're told how to get a new value from the previous value. So you're told something like f of n is equal to f of n minus 1 plus 1. And if we look at it, this is the same sequence. If f of 0 is minus 3, that's exactly what you did here. Then what's f of 1? Well, that's f of 0 plus 1, which is minus 3 plus 1, which is minus 2. And you can keep doing that all the way up. So these are often first introduced even in Algebra 1. These are really common things. And the reason is these are often the way a problem's actually described. If I tell you, for example, that, to pull an example out of the air now, that the number of cases of some disease each week is twice as high as it was the previous week, what that says is you're saying, say, f of 0 is the initial number of cases, say, whatever it might be, 15. And then f of n is twice f of n minus 1. So you're saying essentially that with every new week, twice as many people have this. So f of 1 is twice f of 0, which is 30. F of 2 is twice f of 1, which is 60. And so on, and it grows by doubling each time. Now the question is, well, is there a way to write this more straightforwardly? And this is a really common question that people have here is, can you get from these recurrence relations? Because these are easy to think of, right? I mean, this says exactly what we know about the disease. It doubles every week and it started with 15 cases. This says something true about the sequence. This says exactly what we know about the sequence. It's bigger by 1 each time. Often that's the first thing you see when you look at a sequence. So the question is, how can I get from here to here? How can I get from here to f of n is equal to 15 times 2 to the n? Which is the same thing. Now this is where it depends what level you're at. If, and this is a big if now, if you're an Algebra 1 student, then about the best you could do is to look at a bunch of numbers in a row and see if you see a pattern. So for example, you might look at f of 0 equals minus 3, f of 1 equals minus 2, f of 2 equals minus 1, f of 3 equals 0. And you might say, okay, I think I see where this is going. It looks like I take the input and subtract 3 from it. So I would guess that f of n is equal to n minus 3. And then you could check that that works for a bunch of cases, but how do you prove it always works? If you're in Algebra 1, you don't. If you're in Algebra 1, you say, this seems to work for many numbers, I'll bet this is right. Oops, I just realized this is all out of print. But what do you do if you're a more advanced math student? Well, if the next place you see these things is usually in some sort of introduction to proofs class, or actually sometimes at the beginning of geometry when you're first talking about proofs. Because it turns out there's a way to prove things like this that's built precisely for this sort of problem. And what that is something called mathematical induction. And what mathematical induction says is this. Suppose I have a bunch of different statements which I can index by a lowercase letter. Say I have, statement S0, statement S1, statement S2, all of which are logical statements. They're saying things I think are true. If I can prove that S0 is true, and I can prove that if S sub n is true for any n, then S of n plus 1 is true, then I've proven that, therefore, S sub n is true for all n. This is called mathematical induction. Notice this doesn't actually help you find the answer. It just lets you prove that your answer is right. So for example, in that last problem where we said f of 0 is equal to 3, minus 3 rather, and f of n is equal to f of n minus 1, minus 1 plus 1, we quickly looked at it and said, okay, it looks like f of n is equal to n minus 3. But how do we prove that? So we have to prove two things. So let our statement S0 here, let our statement be S0 is this formula works for number n. So f sub 0 is this formula works for f of 0, s sub 1 is this formula works for f of 1, s sub 2 is this formula works for s sub 2, and so on. This goes on and on and on. Well, let's see. Can we prove that this works for 0? Well, f of 0 is equal to 0 minus 3 is equal to minus 3. True. So yes, this formula works for 0. Now say, suppose f of n is in fact equal to n minus 3 for some n in this sequence. Suppose I know that f of n is in fact up to n is equal to n minus 3 for some n. I don't know for all of them, I just know it for this n. Well, what's f of n minus 1? N plus 1, rather. Well, that should be equal to, according to this formula, f of 1 less f of n plus 1. So this is going to be equal to n minus 3, because for f of n we know that this is true, plus 1, so this is equal to n minus 2. But that's exactly what this formula would have predicted. So this formula works for 0. If it works for some number, it works for the next number. Therefore, it works for everything. And we're done. That's mathematical induction. This is a really useful trick for these sorts of sequence problems. And you can do exactly the same thing with that exponential growth problem I showed you for supposing you have a virus. We hope you don't have a virus. That's why we're all shut-ins at the moment. But so if we don't say that f of 0 is equal to 15, and f of n is equal to f of n minus 1 times 2, remember we quickly said this really looks like f of n is actually equal to 15 times 2 to the n. That really is what that looked like. But is that right? Well, f of 0, according to this formula, is equal to 15 times 2 to the 0, which is 15 times 1, or 15. Check. That works fine. Suppose f of n really is equal to 15 times 2 to the n for some n. Can we prove it for the next number? Well, f of n plus 1 is equal to 15 times 2 to the n times 2 by this formula. Right? It's f of n minus 1. It's f of the next number down, which is f of n in this case, which is 15 times 2 to the n by our assumption, times 2, which is 15 times 2 to the n plus 1, which is exactly what this formula says. So this formula works for all n now by mathematical induction. And again, this is the correct formula. So that's mathematical induction as you see it in a geometry class. This is recurrence relations as you see them in geometry or in an intro to proofs class. And at this point you're saying that's all great, but again, how do you get these formulas? These formulas look really cool. How do I get them? And for that, we actually need something else. For that, we need some linear algebra. So let's take a quick break to see if anybody asks any other questions on Twitter. If anyone asks another question on Twitter, I'll answer that one and go on with this next time. If no one asks a question on Twitter, I'll go on and show how to actually solve these things. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, let's see. We got no new questions on Twitter. So, in principle, I should go on and talk about how to solve these problems. I think I'd like to do that tomorrow. I'll save that for tomorrow's show. So, tomorrow we'll come back and talk about how to actually solve these things, because I'm realizing that's something I should probably not do on the fly. So, but for the moment, I think it may be time to sign off. I see lots of likes, but very few views. So I think it's time to come back tomorrow. Once again, please tweet your math questions to @NightMathRadio. You can do that anytime, not just during the show. I'll answer your questions during the show if you do so. In fact, sometimes it's better to tweet before the show, because if you tweet before the show, I'll have a chance to think it through and have a really good answer for you by the time the show comes on. Well, for the moment, I think it's time to sign off. Stay safe, everybody. Enjoy this weird, strange world with all the math homework and none of the classes. I'll see you all back tomorrow night. We'll keep doing nightly shows as long as the current crisis continues. This has been Nighttime Mathematics Radio. Good night, everybody.